Welcome to a lesson with Dr. Powell. This is part 4 of a lesson entitled A Close Look at Continuity and Limits. Please take a look at parts 1, 2, and 3 before going to part 4, because that's where we're picking up at the end of part 3. In part 1, we talked about some definitions, what codomain is, image, preimage. We talked about this idea of preimage of fuzz, and one way of thinking about what continuity is that at least continuity on domain for a function is that the preimage of fuzziness in the codomain is going to be fuzziness in the domain. Please take a look at part 1 for that description and kind of thought about this idea of delta and epsilon. In part 2, we focused on not continuity of a function on its domain, but at just one single point, what that looked like in terms of epsilons and deltas, this fuzziness idea, and gave an example of that as well. In part 3, we talked about what it meant for a function to be continuous on one side, left continuous or right continuous, and looked at an example of that. And then now in part 4, we're going to talk about limits and how that relates to epsilons and deltas and this idea of fuzziness. So we can say the limit of a function at a point is simply the y value that we need in order to make the function continuous if we can. And it's really supposed to be at a point, but you know what? This is a nice picture. I mean, we're going to be thinking about, so this function right here, oops, we have the wrong y value. Can we change that y value, push it down so that the function right here would be nice and continuous? Or right here is an example of there being a hole. Okay, is there a y value that we can take and put it in right there in order to fill that hole so the function would be continuous? Now, those are nice pictures, like I said, but we also are thinking about this case. Notice how these y values right here are getting close to a particular y value right here. These y values are getting close to this guy. So just kind of like the continuity at a point notion. Is there a y value that we can put in at a point so that the function would be continuous at a point? All right. So basically that's what a limit is in the sense that we're going to be thinking of. It's just the y value that would make continuity at a point. All right. So, but what about if we had a function like this? There is no y value that we can actually put in at this spot that would make the function continuous. This one wouldn't work, that one, no matter which one we pick. So the limit would not exist. So again, we can think a limit is a continuous hole filler if we can. This is really nice when we're taking limit of an expression. Notice right here, we cannot plug in x equals 1. This is not defined to divide by 0. So what does that do to this expression? It makes a hole. All right. So if this expression was equal to so a function output was equal to it, then we would have a hole at x equals 1. All right, so x equals 1 is not in the domain. Well, limits come to save the day, because taking a limit will fill in the hole, will tell us what the y value is that fills in that hole to make it continuous there if it's possible. And in this case it is. The limit does exist. We can, the function does look kind of like this, and we can fill it in. Now how can we see that? So if we take the expression, what we're going to do is we're going to look for something that's algebraically equivalent to it. Factoring, canceling. This guy is equal to this guy, but not really. I mean, it's equal to it in an algebraic sense, right? Because we can simplify to here. but it's not equal in a function sense, in a domain sense. I mean, the domain of this is different than the domain of this. When we algebraically simplify, we can potentially change domain. But how is domain changed? It's usually only changed by like one hole or one spot at a time, maybe putting in a hole or removing a hole or maybe a couple holes or going back and forth. It's just kind of like this like change in just like a little spot here or there. So it's not really so really algebra gives us limits because we're going to play off of this idea that we can change domain when we so if there's a hole and we can't simply, it's not continuous yet, so we can't just simply plug in the x value to see what the y value is, because on an already continuous function, that's all a limit is. It's just plugging in. But if it's not, but if there's a hole, we just do some algebra to change the domains so that we can actually plug in the value, because we have a continuous version of the function. We've actually filled in the hole. So algebraic equivalence has actually taken this expression and filled in its hole so that, well, we can plug in anything we like now. In fact, we can plug in x equals 1 right now and we'll get 2. So we know that the limit of this expression is actually 2. And all we did was kind of that algebraic equivalence to do that. All right, so let's take a look at this example. All right, so x equals 1, that's the spot we're heading. We have a hole there, and our y values, okay, what are they getting close to as our x values are getting close to 1? Hence, we think of a limit, something that, the y values are approaching something. As x approaches 1, what's that place to make that filled in and, that hole. So in this description, epsilons and deltas, it's a lot like, it's basically the same as what we had for continuity of point. I mean, this isn't filled in right now, but if it were, I mean, the description would be about the same, except for one little change. Here I put in this. This is the part that talks about x being inside the some fuzz in the domain centered about 1, going this way and that way. All right, delta, a little distance. Now, in this fuzziness, we actually remove a point. We actually account for there being a hole. We don't want to assume that we can that x has an image at 1, which would be in particular 2. We don't, if it were continuous, right? We don't want to assume that. We want to assume that there's a hole there when we're talking about limits. So little difference from continuity here is we're going to assume that it's not, we don't want to assume the continuity per se that the hole is filled in. So we're going to remove that, but just right here. Notice that we don't put any condition like that over here, just right here. So without this being removed, it would be the same idea as continuity at just one point. In particular, let's just kind of go through what's happening. So what we do is, given some codomain fuzziness, an epsilon going up and down, centered at this point, then we want to find does there exist a delta going this way and that way, so some fuzziness centered right at x equals 1, so that that this domain fuzz, so kind of this open interval going this way and this way centered at 1, if we plug it into the function, it maps completely. Its image is completely contained in this codomain fuzz. And we found, and yes, actually, so in our example, the function is really like x plus 1. That has a slope of 1. So that means epsilon is equal to delta in this case if we're looking at this. So if we let delta be equal to epsilon, we've just found the delta that would work. Okay, so it exists. So saying that delta exists is actually what we need for that description. Okay, so we know that if this condition is satisfied for every epsilon, that is a way of saying that the limit is equal to 2. right? So the limit is going to go in right here. It's what the y values are heading towards. So if this description holds, that means the limit is equal to 2. This is a very precise way of defining and saying mathematically that the limit of a function is something. The limit of this function is 2. Well, precision here. What exactly does that mean without any loopholes in our logical argument? Well, that's this, all right? So with epsilons and deltas. Looks a bit technical, and maybe a lot of people wouldn't like it, but it is precision right here with logic. All right. So taking a look now, let's think about limits on one side. So it's just like right continuous and left continuous, but we have a little notation for that. You see this little plus here, right here? So x approaches 2 of some function, but to the right. So as we're going from the right side, approaching what y value does the function approach as we're coming from the right? It approaches 3. So that we would write down the limit would be 3 from the right side. It's like, what y value would we need to fill in the whole right at x equals 2 that would make this function continuous? So we have to it's kind of like the y value we would redefine the function as being, so it's still a function. Well, the y value is here, but we would move it up here to be right continuous. So the y value we'd move it to would be 3. Now, what about on the left side? The y value we would move, well, we'd keep the y value what it is, which is 1. And so we can denote that limit as x approaches 2 from the left side. So we can kind of think about left continuity and right continuity when we're thinking about limits to the right and to the left. Okay, so let's take a look at this example right here. We have this function, and we were looking at this in a previous segment of this lesson. We have this piecewise function, and it is left continuous right at x equals 1. Notice how it's filled in. Now, we can think about this statement. The limit as x approaches 1 from the left side is going to be equal to 1, and it's filled in right there. Okay, so the epsilon and delta description that we had for previously for this function at x equals 1 is the same description with epsilons and deltas that we can use for the left-hand limit existing of the function at 1. So the left-handed limit exists. You know, the overall limit doesn't exist because there's no y value that would make this function completely continuous, but there is a y value that would make it left continuous. Therefore, the left-hand limit does exist. So if you take a look back in a previous part of this lesson, you'll see this description, how we actually came up with this delta. So there exists a delta, and we found it, we described it right there. That would make all of this work. But the one difference is here, previously, we had 0, and then we had greater than or equal to. We're going to remove the or equal to right here. And that accounts for, in the limit, not requiring that this be filled in yet. So make that a hole right there at x equals 1. So x, we don't want x necessarily to be equal to 1. So we're going to remove that. And I'll just go back there just to kind of show you that in that previous case, we had, in that description, it was right here. Notice we had greater than or equal, or, well, 1 minus x is greater than or equal to 0. Now we just kind of removed that. And that's basically it. So the same description with epsilons and deltas can be used for limits. We just kind of modify this just slightly, just to account for holes, but that's basically it. And that is our lesson. Thank you for watching. That was parts 1, 2, 3, and 4. Thank you.